Okay, stationary points and points of inflection. So when I look at this graph, which is a parabola, I'm going to see there's two things happening. Okay. On this side, as it's going down, as y is decreasing, we see our function is decreasing. Okay, our gradient is negative. As soon as I move to the other side, we have an increasing function. So for every x value, my y value is getting higher. Okay, so increasing, and we have a gradient that is positive. Here in the middle, we have a stationary point. In the parabola, we also know it as our turning point. So we have a gradient that's negative, decreasing function. We have a gradient that's positive, increasing function. So that is like a little side note to remember. Okay. Then with our next section, we're going to talk about concavity. Okay. So function can either be 1, concave up, or B, concave down. So when a function is concave up is when the function lies above the tangent. So now you can see there's like a bunch of tangents drawn over here, and our function is lying on top of them. Okay. When it's concave down, it means the function lies below the tangents. So here's a bunch of tangents, and our function is below it. Okay. So no matter where I draw my tangents, if my function lies above, like on my tangent, the function will be concave up. And then on our other hand, no matter where I draw my tangent, if my function lies below or under my tangent, the function will be concave down. So let's say a smiley face parabola will always be concave up, up on the tangents. And frowny face, a sad face, -1, would be below my tangent, concave down, below. So with this being said, sometimes our concavity can change. And this is where we get to our points of inflection. So quote unquote, a point of inflection is a point on a curve where the concavity changes either from concave up to concave down or vice versa. Now, how can we get this? Now, the second derivative can be used to determine the concavity of a function. Now, how do we find it? We have already worked with our first derivatives. So finding our second derivative, you derive 2 times. So usually we would have our normal fx function, then our first derivative, like you note, first derivative, and then our second derivative, which I note with 2. Okay, so you derive once to get to my first derivative, and to get to my second derivative, you derive your first derivative. Okay, so now is the important part. So if my second derivative is 1 bigger than 0, the curve is concave up. If my second derivative is smaller than 0, the curve is concave down. And if my second derivative is equal to 0, that means that's my point of inflection where it changes. So if you look at these diagrams, you'll see I am starting with this one, then switching, going over to that one. Okay, so first I have concave down, then my point of inflection where my second derivative is equal to 0, and then I have my concave up. Now with this one I have first concave up, then I have concave down, and that you'll see when you work with your points of inflection. So if I go over to an example, okay, so given that fx equals x cubed plus 18x squared minus 4x plus 4, show that there is a point of inflection when x equals -6. Now, first thing I need to remember is point of inflection is when my second derivative is equal to 0. So first things first, I need to find my second derivative. So when I derive once, I get 3x squared plus 36x minus 4. And then I need to derive this one again to get to my second derivative, which leaves me with 6x plus 36. Now, my point of inflection occurs when my second derivative is equal to 0. So now I substitute my second derivative for 0. Like you can see, it was this, now it's 0. And then I need to solve x. So when I solve x, I find that x is equal to -6. So I just proved that we have a point of inflection when x is equal to -6. But now a little bit more information. Now let me check if the function is first concave down or concave up. So how I'm going to do that is, if I work on my line, I have at one point I have -6, then I have -7, and on the other side I have -5. So I'm going to substitute these into my second derivative. So first I'm going to start with one on the left side, which is -7. Substitute it in, and I get my second derivative of -7 is equal to -6, which means it is concave down. Now, if I substitute in -8, I'm going to get -12, concave down. If I substitute now on the right side, -5, I'm going to get 6, which means it's concave up. And if I substitute in -4, I get 12, which means it is concave up. Now, at a point of inflection occurs at x equals -6. So that's everything I needed to prove to show that it is a concave up, concave down, and where my point of inflection is. Okay.